Hello, this is Emad Mirabi, and this is the second session of the 7th grade physics. In this session, we're going to cover the following topics: units of energy, work definition and calculation, which means the definition of work and calculation of work, and then the kinetic energy. Okay, let's start. What is energy? Energy is the ability to do work or cause change. Everything we do, for example, running, eating, heating our homes, uses energy. Everything we do needs energy. Okay. Common units of energy. One of the common units of energy is joule. The most common units of energy is joule. It is named after the scientist James Prescott Joule. He was a British physicist. Okay. It takes about 1 joule to lift a small apple 1 meter up. If you lift an apple 1 meter up, you have worked 1 joule. This takes 1 joule of energy to do this work. Okay, let's continue. Calorie, often used for food energy. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So in the heating of water, if you heat 1 gram of water and the temperature decreases 1 degree Celsius, we have used 1 calorie of heat. Okay. In food labels, we usually talk about calories with capital C, which are actually kilocalories. So afterwards we call it little calorie and big calorie. A big calorie is written by capital C, a little calorie is written by lowercase c. So big calorie is thousands of lowercase, or big calorie is thousands little calorie. Small calorie. Okay, so 1 food calorie is equal to thousands calorie, which is about 4,184 joules. So based on this we can say 1 calorie, let me write it with lowercase c. So 1 calorie is equal to 4.184 joule. So calorie and joule are units of energy. Another unit is kilojoule, which means thousands joule, of course. Kilo is a prefix. Kilo is a prefix of unit. It means thousands. A bigger version of a joule is kilojoule. Okay, kilojoule means thousands joule. Sometimes used in food labels too, especially in other countries. Okay, let's have an example. Example of kilojoule is a banana might have 400 kilojoule of energy. Another example is a single matchstick releases around 1,000 joules or 1 kilojoule of heat when it burns completely. So when you burn 1 matchstick completely, it gives 1 kilojoule of heat. So this gives us a rough estimate of what is a kilojoule is, or how much. For example, when we say a ripe banana gives 400 kilojoule of energy, we'll have a rough estimation of what is the amount of kilojoule. Of course, comparing this kilojoule with the 1 joule example of 1 joule above, we see that heat energy is much greater than mechanical energy. So 1 matchstick burns completely, gives 1 kilojoule of energy. but one small apple raised 1 meter is this process, or this mechanical energy is 1 joule. So heat energy is much greater than mechanical energy. Let's go forward with some example, doing some example. Energy content of a food is 20 calories per gram. If we eat 50 grams of this food, how much energy do we get in calorie and joule? Okay, so we can solve this question like this. 50 gram, okay, here. So 50 gram of this food. What is the energy content? The energy content is 20 calorie. This is big calorie because it's written with capital C. 20 calorie per gram. So this gram cancels this gram. Then we can say after eating this food, we have taken thousands big calorie. Or if we change this big calorie to a small calorie, we can say 1 million, we have taken 1 million calorie, lowercase c. And then applying the change, let's do the unit change. We learned that 1 calorie is equal to 4.184 joule. And therefore, if we multiply, so because every calorie is 4.184 joule, we need to multiply it by 4.184 to find the energy in joule. So it will be 4.184, 3 zeros, which means 4,184,000 joule. Or we can say 4,184 kilojoule. This is the amount of energy we get in big calorie, in small calorie, in joule or kilojoule. How did I change from joule to kilojoule? I divided by 1,000. Okay, let's talk about work. Work happens when a force is used to move something over a distance. If you push or pull something and it moves, you're doing work. If there is no movement, no work is done, even if you try hard. So this is the formula for work. Work equals force times distance. Usually it's written like this. W equals F times D. W represents work, F represents force, and D represents distance. So work is measured in joules. So this is work. What is the unit of work? It is joule, the same as energy. F is force. What is the unit of force? It is in Newton. I'll talk about force in the upcoming slide. This is distance, and the unit of distance is meter. Sometimes joule can be, instead of joule, sometimes we can write Newton meter, which means Newton times meter will be joule. Okay. What is force? Force is a push or pull on an object. Force can make things move, stop, speed up, slow down, or change direction. Examples of force: pushing a door open, pulling a wagon, kicking a soccer ball. These are examples of force. Force is measured in newtons, and it's usually denoted by a capital N. force needed to lift 2 eggs is about 1 Newton. To have an approximation, each egg is 50 gram, so 2 eggs is 100 gram. 100 gram of mass will be equal to 1 Newton of force. So you have 2 eggs, for example, in a very light nylon. If you want to lift it, what is the force needed to lift it? The force is 1 Newton. Okay, let's go back to the work formula. Work formula was W equals F times D. Work equals force times distance. So force is a push or pull. What is the unit of it? Newton. A distance was how far something moves. The unit of distance is meter. Work is the force used over distance. So the unit of work is joule. Joule is usually denoted by a capital J. Okay, you apply it. Let's do an example. You apply 10 newtons force to move a box 2 meters across the floor. How much work is done? So the problem is something like this. This is a box. This is a box. We are applying a force equal to 10 Newton. And it moves 2 meters. For example, it comes here. For example, it comes here. This is the distance of 2 meters. So we apply the formula work equals force times distance. What is force? It is 10 Newton. All the units are in SI units, or the given units. We said force, the unit of force is Newton, the unit of distance is meter. All of them are standard units. So F is 10, distance is 2. Therefore, the final answer is 20. What is the unit for 20? The unit is joule. Because in physics, most of the quantities have units. So we cannot say work is 20 only. Work is 20 joule. Okay, how much work is done? 20 joule. Okay, if we lifted 20 Newton back from floor up to 1.5 meter height, how much work is done? This is another example. So this is a bag. What is the weight of it? 20 Newton. So because it's 20 Newton, the weight of it is 20 Newton, we need 20 Newton to overcome. We need 20 Newton to overcome this weight of this bag. So we are applying 20 Newton of force to raise 1.5 meters. So this goes up to height of 1.5 meter. For example, here again we can apply the work formula. So the work formula says force times distance. 20 times 1.5 is 30. 30 joules of work is needed to raise this bag to the height of 1.5 meter. Okay. In the previous example, if we keep the bag up for 1 minute, motionless, how much work is done? The weight of the bag was 20 Newton, of course. We say because it is motionless, because it is stated that it is motionless, so there is no distance. Force has not made any movements. Force has not caused any movements. Distance is 0, therefore work is equal to force times distance, which is 0. So whenever distance is 0, whenever distance is 0, because W is equal to F times D, W is 0. So work is 0. So scientifically we say, of course, it is in contrast with usual terminology. Scientifically we say that the person who keeps something up, even though it might be heavy, we say that it has done no work. Even if we keep up a very heavy thing but motionless, we have not done any work. So work needs both force and distance. I mean, the force must have caused some movement. Okay, let's continue. Kinetic energy is the energy of motion. So we talked about units of energy, we talked about work. Now we want to talk about kinetic energy. As the name says, kinetic means motion. So the energy in moving particles, the energy in moving particle is kinetic energy. Okay, kinetic energy is the energy of motion. Any object that is moving has kinetic energy. The faster something moves, or the heavier it is, the more kinetic energy it has. So the faster something moves or heavier it is, more kinetic energy it has, because kinetic energy depends on the mass. Also it depends on the velocity. Okay. Examples of kinetic energy. A rolling soccer ball has kinetic energy. Why? Because it's moving. Flying bird has kinetic energy because it's moving. A moving car has kinetic energy. A kid sliding down a slide has kinetic energy. Even air particles moving, like wind, it has kinetic energy. The formula for kinetic energy is half of mv squared, which means it involves both mass and speed, but speed squared. So 1/2 times mass times speed squared. M is mass measured in kilogram, V is speed or velocity in meter per second. Kinetic Ke represents kinetic energy, is measured in joule. If mass is in kilogram and speed in meter per second, the kinetic energy will be measured in joule. If other units are used, it's a different story. So we need sometimes in physics to do a unit change. We need to apply or perform unit change sometimes in physics. Okay, the speed is squared in this formula. Pay attention to the power of 2. Power of 2 means, so for 7th grade students, it's important to know that the power is defined like this. A to the second power is A times A. Or A, it is also read A squared. A squared is a number multiplied by itself. Okay, what is this? A to the third power, or A cubed. A cubed means A times A times A. So the velocity or speed has a second power, which means the speed is squared. So if you double the speed, the energy increased by a factor of 4. It is important to pay attention to this. Okay. We have a parked car. Does it move? No. So does it have kinetic energy? No. A rolling toy car. Does it move? Yes. So it has kinetic energy. So it's a matter of moving or not, because the formula says usually kinetic energy is denoted by K alone, sometimes Ke or sometimes K alone. K alone is more usual. Okay. K is equal to half of mv squared. This is the formula for kinetic energy. Can the mass be zero? No. Even this tiniest particles have mass. For example, a particle of the gas have mass. So mass cannot be zero. The only way we can make k0 is v. When the speed is zero or the object is motionless, the kinetic energy is zero. So we're talking about if something is moving or not, and if the answer is no kinetic energy, we have no kinetic energy. And if it is moving, it has kinetic energy. That's all. So if k is zero, if and only if v is zero, because mass, all objects have masses, though small or big, but it is non-zero. Okay. A running dog, it is moving. Is it moving? Yes. Does it have kinetic energy? Yes. A sleeping cat, does it move? No. Does it have kinetic energy? No. So v relates to k, which means moving objects have kinetic energy. Let's continue with an example. If the speed of a vehicle increased by a factor of 3, how does its kinetic energy change? So I can write it like this. v2 over v1 is 3. So because v2 means the velocity or speed after the change, v1 is the initial velocity. So v2 over v1 is 3 because it has increased by a factor of 3. And then the question says, how does the kinetic energy change? What is k2 over k1? We can apply the formula like this. k2 over k1 is equal to half of v22 over half of v12. So half and half cancels away. Mass of the object is constant. So we can write this as v2 over v1 squared. So v2 over v1 is 3. 3 squared is 9. Therefore, we can say kinetic energy increases by a factor of 9. So let me write it here. So kinetic energy increases by a factor of 9. By a factor of 9, it increases. Or we can say, if we want to talk about percent change or the percent increase, we can apply the percent change formula. If we apply the percent change formula, it will be an 800% increase in velocity, in kinetic energy. 800% increase in kinetic energy. How I got 800%? I applied the percent change formula. What was the percent change? Percent change formula was the final value minus initial value over initial value times 100%. This is the percent change formula. Okay, if we apply this formula and k2 over k1 is 9, 9 minus 1 is 8, 8 times 100 is 80% increase in kinetic energy. Okay, let's do another example. There is a truck filled with water. If the mass of this truck decreases 30% and speed doubles, how does this kinetic energy change? So this time we have m2 over m1. So mass of truck decreased 30%. If something decreases 30%, we can say it has multiplied by 0.7 or 7/10. Again, I found this relation by applying the percent change formula, but more quickly. And it says the speed doubles. The speed doubles, okay? And therefore, let me apply it into the kinetic energy formula. Kinetic energy formula says half of m v squared, half of m v squared. Half and half cancels away, but m2 over m1 here must be multiplied by v2 over v1 squared. So k2 over k1 will be equal to 0.7 times 2 squared. 4 times 7 is 28. 28 with one decimal place is 2.8. So we can say kinetic energy increases by a factor of 2.8. Let me write it. Kinetic energy increases by factor of 2.8. Or we can say it increases 180%, or 180% increase in kinetic energy. So again, this percent change, we can either say it is multiplied by 2.8, or we can say 180% increase. It has experienced 180% increase. Okay, it is enough for this session. We'll continue the topics of energy, potential energy, and the stuff in the upcoming session. Bye bye for now.